All right, welcome back. Today we are going to be looking at our next little section in stoichiometry, specifically looking at something called the limiting or excess reagents. So basically what this is that every single chemical reaction, there's always going to be something that's going to limit how much products we can actually form. And that's what we have right here. So a chemical reaction is limited by the reactant that is completely used up or consumed first. So the analogy we kind of like to use to kind of explain this one is like if you're making, in this case right here, a ham and cheese sandwich. All right, so for example, if we need 2 slices of bread, 1 piece of cheese, and 1 piece of ham to make one complete sandwich, and the question asks how many complete, keyword here is complete, sandwiches can we make if we had 8 slices of ham, 7 slices of cheese, and 18 slices of bread. We know we need 2 slices, so if we go 18 divided by 2 equals 9. So when we look at it, well, with the ham we can complete 8. With the cheese we can only complete 7. With the bread we complete 9. So obviously the amount of complete ones we can make is only 7. That is because the thing that limits the amount of complete sandwiches produced is going to be the cheese because we have less of it. So this is going to be called the limiting reagent because as we're making stuff, this is going to get used up first. And as soon as it's completely used up, well, we can no longer make our complete sandwiches. Or if this was a chemical reaction, as soon as it is used up, well, the reaction is going to stop because one of the reactants is completely used up. So of course, in this analogy, the reactants that are left over, we have bread and ham, and we are going to call these the excess reagents because there are more of them, so they are in excess. So that is what we're going to be looking at right now. Is we're going to be looking at reactions in which we're going to be able to calculate the limiting reagent. So a lot of questions that we have seen right now, you would have looked at words like it'll say, 5 grams of this reacts with excess of something else. So if you notice a lot of those words like reacting with excess, that is because one of the reagents are in such amount of excess that we know it's not going to be limiting. So now we're going to be moving towards actually looking at limiting reagent questions. So of course, when the limiting reagent is consumed, no more products can be formed, so the reaction is going to stop. So the definition of a limiting reagent is we have right here. So it's the reactant or the reagent that is completely consumed in a reaction. So the limiting reagent determines the maximum amount of quantity, the product or products that can be formed. Because as soon as this is used up, reaction stops. So as soon as this reagent is completely used up, however much product that we had formed, well, we can't get any more. And of course, the excess is going to be the reagent that remains after the reactant has taken place. So the key thing is right now, how are we going to identify these limiting reagent questions compared to the types of stoichiometry that we've done so far? Well, in this one right here, the limiting reagent questions, you're going to be given enough information to determine the amounts of both reactants. So that means there's going to be 2 givens. So that is how we're going to recognize our limiting reagent questions. There's still going to be only 1 required substance though. That's it. But we're going to be given information about 2 of the reagents. So when we look at our steps for solving our limiting reagents questions, you're going to notice that it is very reminiscent of all the stoichiometry problems that we have that you have done so far. So step 1, write the complete and balanced chemical equation and states of matter. That is what we've done so far with all 3 different forms of stoichiometry. Part 2 is determine the number of moles of both reactants. Now, normally it was only 1 given, whereas this one, because we're going to be given 2, is going to determine the number of moles of both of them. All right, so we're going to be working with 2 givens. Now, step number 3, this is the new step, but it's only the second half of it's going to be new. So step 3, we're going to determine the number of moles of our wanted substance or required using our mole ratio, but for both reactants. So we're going to do that calculation twice. Now, what you're looking for is the one that gives you the lowest number of moles of your wanted species. This is your limiting reagent, and we use the lowest number from step 3 in step 4 to solve the question. So yes, there's just a little more work that needs to be done, But for the most part, as long as we can get to step 3 where you find the number of moles of your wanted substance twice and then use the lowest number for step 4, you're going to be okay. So let's look at one of the examples on the next page. Alright, so for this one right here, it says, what would be the limiting reagent in a reaction of 80 grams of copper and 25 grams of sulfur? What is the maximum amount of copper 1 sulfide that can be produced? So it is giving us a little bit of information here. This is a formation reaction because we have elemental copper and elemental sulfur reacting. And the product is copper 1 sulfide. All right, so step number 1 is balanced chemical equation. So in this case right here, we have copper, which is just Cu solid, plus sulfur. So remember, sulfur is S8. This is also a solid. They react, it says, producing copper 1 sulfide. So of course, this one right here, you can do your drop and swap up at the top. So copper 1 is 1 plus. Sulfide, when you look at that on your periodic table, it's S2 minus. So the drop and swap, the 2 is going to go in front of copper, the 1 goes in front of sulfur. So we're left with Cu2S. And ionic compound, so also solid. Now, of course, we do need to balance, so we have an 8 in front of copper 1 sulfide to get our 8 sulfurs. Now, in our next case, this creates 16 coppers, so we need the coefficient of 16 in front of copper right here, and we are done. So that is step 1, balanced chemical equation, done. Now, for our step 2, it is find the number of moles of your given substance. So we have 2 givens here. And only 1 wanted. So you need to organize your work just to kind of make sure you are doing them right. So what I like to do is just kind of separate, especially for step 2 and 3, is kind of do like a little T-chart where we have copper, solid, and then organize it, and then we have sulfur over here. Now you don't need to do it this way, but it definitely helps. So where copper we have 80 grams, so number of moles of copper, or our given at this point, is mass over molar mass. So our mass is 80.0 grams. The molar mass for copper is 63.55 grams per mole, and we have 1.25885 mole. So that is for copper. Now for sulfur, we're going to do the same thing. Number of moles of sulfur is equal to mass over molar mass. So the mass of sulfur was 25.0 grams. The molar mass for sulfur, it is S8, so we take the molar mass of sulfur from a periodic table, multiply it by 8, and we get 256.56 grams per mole. And this equals out to 0.097443 moles. So that is step 2. Find the number of moles of both our givens. Now step 3 is find the number of moles of our wanted using the mole ratio. So because we have 2 givens, both copper and sulfur, we're going to do this calculation twice again. So remember our formula, number of moles of wanted is equal to number of moles, in this case of our given, is going to be copper times our mole ratio, and same thing for sulfur, but we'll get to that later. So number of moles of our copper, we just calculate 1.25885 mole, times our mole ratio. So the mole ratio right here is wanted over given. So wanted is copper 2 sulfide, so the mole ratio is 8. The given for our copper is 16, so 8 over 16. And we have number of moles for our wanted is 0.629426 mole. So that is for our copper. Now we're going to do the exact same thing for our sulfur. So in this case right here, number of moles of our wanted is just equal to number of moles of our sulfur times our mole ratio. So that is our 0.0974443 mole times our mole ratio, so wanted 8, over given this time, because it's sulfur, the coefficient in front of sulfur is 1. So when we do this, it's 0.77954448 mole. All right. So step 4 is solve the question. But we have two values right here. So we need to pick the one that we're going to use. So when you look at the previous page, which I'm going to go back to it there now, it says, once it actually goes back, there we go. It says the one that gives you the lowest number of moles is your limiting reagent, and that's going to limit the amount of products being formed. So we use our limiting reagent from step 3 to solve our question. So that means we look at the number that is lowest. So this right here is our limiting reagent. So this number we're going to use, which means that we can scratch out this work right here, and this is the excess, because we're not going to need it. So we use the number that is lowest to complete our question. So mass, on this case right here, is copper 1 sulfide, is equal to number of moles times molar mass. So we take the lowest number of moles calculated in step 3, multiply by the molar mass, and we are left with 3 significant digits. We have 100 grams. So that is how we solve these limiting reagent type questions, where you have to make sure that we go through all the steps that we have done before, but just making sure we use the one with the lowest number of moles from step 3. So you don't need to organize it like this. I just find it is easier to kind of do this T-chart type thing, where we have one of our reagents on one side, one of the reagents on the other, just so I know that everything under here is my calculations for the copper, everything under here was the calculations for the sulfur, and it just kind of makes it a little easier to organize information like that. Now you don't need to do it that way, it's completely up to you on how you solve these here. So I'm going to do one more with you guys, and then I'm just going to kind of give you the answers for the next few, just so you can do it. But this is another typical limiting reagent question, where in this case right here, the balanced chemical equation is already given to you, and it's divided up into part A and part B. So part A, it just asks what is the limiting reagent or reactant if 4 grams of chromium and 6 grams of iron 2 nitrate were reacted, and then part B is what would be the expected mass of iron formed. So in this case right here, I'm not going to rewrite the balanced chemical equation because we are given 2, and this is our wanted for part B. So we can just kind of put 2 of these together. So basically part A, we don't need to start off with our balanced chemical equation. We can jump straight into the calculations. So our 2 given substances, we have chromium and we have iron 2 nitrate. Now, we have 4 grams of chromium and 6 grams of iron 2 nitrate. So what we have, number of moles of chromium, or wanted in this case, or given, sorry, given, is mass over molar mass because we are given that. So we have 4.0 grams of chromium over the molar mass of chromium, which is 52.00 grams per mole, and we are left with 0.076923 moles. So that is for chromium. Now our iron 2 nitrate, same thing because we were given our mass. We do our formula mass over molar mass. In this case it's 6.0 grams. divide by the molar mass of iron 2 nitrate. We got 1 iron, 2 nitrogens, 6 oxygens. So we add all those together and we get 179.87 grams per mole. So we would divide 6 grams by that and we get 0.033357 mole. Now, from here, it does look like our iron 3 nitrate is definitely our smaller one, but we still need to go through that whole step of doing our mole ratio thing just to make sure. So we go with our chromium, number of moles of our wanted is equal to number of moles of our given times our mole ratio. So that is equal to 0.076923 mole times our mole ratio. Wanted in front of iron is 1 over given in front of chromium, 1. And we get 0.076923. And we're going to do the exact same thing over here for our iron 2 nitrate. Number of moles of our wanted is equal to number of moles of our given times our mole ratio. So that is equal to what we just calculated times our mole ratio. So wanted in front of iron is 1 over given, also 1. And we get 0.033357 moles. So we can answer part A right now because it asks for what will be the limiting reagent for this particular reaction. So the limiting reagent is the one that will produce the fewest number of moles of our wanted substance. So we have our limiting reagent right here, which means our chromium is in excess reagent. So this is just shorthand for excess. Instead of writing out EXESS, you can just write X and S, just kind of shorthand for excess, and obviously LR is for limiting reagent. So part B, what is the expected mass? Well, mass is equal to number of moles times molar mass. So we take the number of moles of our limiting reagent and we multiply by the molar mass of our wanted substance, which is just iron solid, and the molar mass is straight from the periodic table, 55.85 grams per mole. And we get 1.86 grams, which we are going to simplify into 1.9 for 2 significant digits. And that is how we solve our second limiting reagent question. So from here you can kind of tell that there's nothing really kind of new with our limiting excess reagent questions. All we are just adding some extra calculations, just trying to get the number of moles of either our limiting or our excess reagent, and that is just kind of adding, well, getting the number of moles you're given twice and also getting the number of moles of your wanted twice. But as long as you can follow these steps, you should be fine. Now, there are a few more examples here, so actually 3 more if you are looking at the notes. We got example 3, 4, and 5. So example 3 is a solution stoichiometry question. How you actually solve this here is going to be no different from all the other ones. As long as you have your balanced chemical equation and everything like that, you should be fine. Now, I would like you guys to pause this video on your own and see if you can get the answer. The only thing I am going to help you out with first is the first step, and that is the balanced chemical equation. Because we have mercury 1 chloride, which is just HgCl, and it says that it is a solution, so that means it's AQ, and it's reacting with a solution of aluminum sulfide. So aluminum is Al3+, sulfide is S2-. When we do the drop-in swap, it's Al2S3. Now it also says this is a solution, so it is AQ. So this is a double replacement reaction where we're going to get aluminum chloride form and then mercury 1 sulfide. So aluminum chloride, aluminum has a 3+ charge, chlorine has a 1- charge, so we get AlCl3. This is going to be aqueous. And finally, our mercury 1 sulfide is going to be Hg2S. When you check your solubility charts, this should be solid. Now, of course, balancing this one right here, you need to have a 6 in front of mercury 1 chloride, a 1 in front of here, 2, and a 3 to get them all balanced. And then, of course, this is given, this is given, what mass of the precipitate, this is the wanted. So if you already paused the video and worked through this one, just go ahead and see if you can get the rest. But anyway, so the steps 2, 3, and 4 are going to be coming up now in about 3 seconds. So please pause the video and see if you can get this one on your own. All right, and what you should get should look something like this. So we have number of moles that are given for mercury chloride, mercury 1 chloride, and aluminum sulfide will look like this. So number of moles, just C times V. And we get our respective moles for both. And then finally, number of moles are wanted. Same thing, we do this calculation twice. Number of moles are given times the mole ratio. So for mercury chloride, the mole ratio is 3/6, which we have right here. To give us number of moles are wanted, 0.0200. And for the aluminum sulfide, the mole ratio is 3/1. So that's why we have that, and we get 0.150. So we find out that the moles from mercury 1 chloride is our limiting reagent. We get our aluminum sulfide. This is our excess. So we scratch that out because we don't use that. We only use our limiting reagent, number of moles down for our final, which is mass is just equal to number of moles times molar mass. And we get 8.67. So that is number 3. Now, as for number 4 and 5, same thing. Even if you look at the answer key that I have posted up online, I don't have step by step there, but you definitely want to go through these here and see if you can get them, because what we have for 4, you should find the limiting reagent should equal silver nitrate, so make sure you do this, and the answer, we get mass is equal to 4.52 grams. And for example 5, the limiting reagent should end up being zinc, and the answer mass should be 45 grams. So work through 4 and 5. Make sure you get these answers. If you do not, make sure to let me know so we can go through it one-on-one through a Google Meet or something like that. And of course, make sure to work through the limiting reagent questions inside of your workbook just so you're up on this stuff. Because limiting reagents questions definitely are up there. You should be able to get these, and they can fall into any type of stoichiometry. All right. So our next one, we are on something called titration analysis, and that is basically almost close to the end of Chem 20. And after that, we have a small little lesson on acid-base titration curves, where it's mostly just kind of a nice-to-know type thing. There will be no calculations with it. So we have one more section with calculations, one just a little bit of theory, and Chem 20 is complete. So I'll see you guys next week, next lesson for the titration analysis.